Well, good afternoon, grade 11s. All right, this is lesson 2 for the dynamics unit. And yeah, we're going to be talking about, I'll just go over a couple things we talked about yesterday, but also we're going to talk about Newton's second law mostly today. Okay, so I just want to point out something with the homework here. I actually I mentioned this today to the students in class that I said, am I in the right file here? Semester 1, 2020. Yeah, that's you guys. All right, I thought I had marked this off already, but anyway, just let me put your mind at ease, okay? We are going to do worksheets instead. Okay, so you do not have to do this. Now, if you care for additional practice, sometimes the rare sort of student will come to me and say, yeah, like, can I get more practice questions to do just for more, just so they can get ready for the test a little more thoroughly or whatever. You can do this. The text, I'll tell you, is optional. I don't need to see it from you. Okay, for the first couple of lessons at least. We might get back to it later. I'm also going to go a little bit out of order. So here we're going to cross these guys out as well, but I'm actually going to do friction. We're going to do that today. Okay, so I'm going to move friction up the queue. Also gravity, near Earth gravity. And we'll get rid of these guys. We're going to put that up in the queue also. So I've got to reorganize, and maybe I'll actually take some time and put a new outline together. But yeah, do not do the textbook homework for a little while. Okay, guys, it's going to be worksheets. Okay, and you'll see when you get them. All right, well, without further ado, let's look at today's lesson. Okay, so yes, the homework sheet from yesterday, I know some people are asking. So there was several questions here. I don't know if that's going to load or not. Huh, it says I'm not online. I think I'm online. I'm going to need to start this over now. Let's try a different page. Yeah, it's kind of important that I synchronize these notes. I'm synchronizing my other notes. Yeah, no problem. There you go. All right, well, thank goodness. Okay, no time for technical difficulty at this point. All right, so take a look. Here you can see that we have a bunch of questions here. I will post answers to these questions. Most of them are very straightforward. I know there's a number of them there. Some of them are American units, miles per hour. You're going to need to convert. Oh, it converted it for you. Pardon me, 91 point. Yeah, so it did the conversion for you. Always use standard units. Must always use standard units, meters, seconds, okay, and so on. All right, so anyway, I'm going to give you a chance to do these questions. Most of them are very short, okay, so you shouldn't be spending a whole lot of time doing these questions. No diagrams are necessary to answer those ones, but there's more coming, so I want to talk to you about that. All right, so here I prepared some notes for you, and I'm going to add to these notes while we're talking here. Okay, so Newton's second law of motion says that when a force, an unbalanced force, acts on an object, the object will accelerate in the direction of that unbalanced force. And the acceleration you get will equal, the sum of whatever forces are acting on the object divided by the mass of that object, okay? And that's it. So the net force represents the sum of the forces acting on mass m. Shout out to Luna here, okay? Notice what it says, the sum of all the forces acting on mass m. And a is the acceleration of mass m. And of course, m is just the mass of the object. Now, a couple of things. Let's take care of gravity near Earth. Now, I mentioned this one already, so I'm just going to quickly go over it again because I didn't really get a lot of time to explain it to you. We know that the acceleration due to gravity, anywhere you walk on the surface of the planet, anywhere you can go, okay, is 9.8 meters per second squared down. And what we do is we give that, in this unit, we're going to give that a special letter. Instead of just calling it A for acceleration, we're going to call it G for gravitational acceleration. Okay? So sometimes you've heard people say somebody's accelerating at 1g. Well, that means 9.8 meters per second squared. 2g would be 19.6 and so on. Now, therefore, the force of gravity on your body, okay, is actually mass times 9.8, and that is the force of gravity on your body. Okay? Now, that is technically called your weight. So weight is a force. It's measured in newtons, okay? And we unfortunately use that word, it's like a misnomer when we use it. Usually when people ask you, like if your doctor says, I need to know your weight, what they mean is your mass, okay? And you answer in pounds or kilograms. That's actually your mass, that's M. Mass times 9.8 is your real weight, and to explain to you the difference, like if you went to the moon, your mass would stay the same, like your body is made up of the same amount of matter when you go on the moon, that's your mass, but your weight would change on the moon. Okay, you'd have just a small fraction of your weight because gravity's weaker there. So weight is the force of gravity on your body. It's always down, force of gravity on your body, just straight down. And it doesn't matter where you're standing on, I'm sorry you flat earthers, but where you're standing on a round earth. Let's draw a little guy here. You will feel the force of gravity downwards no matter where you're standing, you know, straight down towards the center of the earth. Okay? Now, I just want a little note about standing on a bathroom scale. Okay, so if you're standing on a scale, so here I talk about scales, what scales do is they measure your force of gravity and then they divide it by 9.8. Okay, and that will report, therefore, your mass. Okay, if you take the force of gravity and divide it by 9.8, you will get mass in kilograms, and that's how scales typically work. All right, so gravity. Gravity is always there, and so we always have to worry about gravity in various types of problems that we're going to be doing. Now, let's talk about contact forces. The first contact force I would like to talk to you about is something called surface contact. So, you know, right now, you're for sure not floating in the air, I'm guessing. You're in contact with a surface, whether it's the floor or the couch or whatever it is you're sitting on. Could be your bed, whatever it is. Now, we call contact with the surface, it's called the normal force. Now, I'm going to explain what that word means in a moment. But let me explain first why, what surfaces do. When a surface is touched on an object, all it can do is push on that object. It can't pull. The floor can't pull you down. It can only push you in the upward direction. And that's what it's doing to support you right now. Okay? And we label the, like on a diagram like this, where we see an object here. Here's an object that has two forces acting on it. Gravity, I'll just color it red. Gravity's acting downwards because that's what gravity does. So that's the force of gravity. That's the weight of the object. What prevents the object from falling, though, let's say it's sitting on a tabletop or sitting on the floor, it doesn't really matter. But what prevents it from falling, sorry, I meant to use blue. I don't know why it's not working. Now it's working, okay. So what prevents the object from falling is this balancing force from the surface that we call the normal force, okay? Now the normal force is the surface pushing up on the object. And these two forces balance when an object's just resting on the table. If they're, whoa, that's thick. Okay, let's fix that thickness. When these forces are in balance, okay, when they're in balance, in other words, when there's like, you know, the normal force is equal to, you know, let's say 100 newtons up and gravity's 100 newtons down. They're in balance, they cancel out, and the object doesn't move because the net force is 0 on an object like that. Okay, so we call Fn is surface contact force. Okay, the normal force. Now, why normal? Here, let me explain. Why normal? It's because in math, the word normal means perpendicular. Okay, now what they mean by that in this case is the normal force is perpendicular to the surface that's exerting a force on the object. And that's why it's called normal force, because it's perpendicular. Okay, because it's perpendicular to the surface. Now what that means is if you were to take, like, for example, here, I'll just draw it over here. If you were to take like your tabletop and just incline it like a, say a piece of wood that's tilted or slanted, or you're sitting on a hill or whatever it is, and here's your object resting on the hill, well, gravity would still be straight down because gravity is always straight down, but the normal force would actually be perpendicular, okay, to the surface itself. So that would be 90 degrees, okay? It's perpendicular to the surface of contact, which in this case is a tilted hill. So the normal force would be, I'm sorry, I didn't mean to write it like that. All right, so the normal force would be like that, perpendicular to the surface. And that's why it's called normal. It's because it must be perpendicular to the surface. Now in grade 11, like all the questions, the normal force is pretty much always perpendicular to the surface. So you don't have to, or sorry, it's almost always horizontal, so it's just straight up. But you can have a tilted surface, and the normal force can change orientation when that happens. Okay, so that's called the normal force. Now, by the way, I show you an example of a box sitting on a table here. Okay, if you read the caption, it says the normal force is perpendicular to the surfaces in contact. That's why we call it normal. Now, if you like, what the box does is it pushes down on the table, okay, with a surface contact. So it's pushing down, but the table pushes up, okay, on our box. And that's what we mean by the normal force on the box, is that upward force of the table pushing up. Now, Newton's third law comes into play. The box pushes down on the table pushes up on the box, and those two forces are what Newton was talking about when he said for every action there's an equal and opposite reaction. Okay. All right. So now, what other kinds of forces are we going to talk about? We'll talk about applied forces. Now, applied forces are when some external actor, could be an agent, like not an agent. What am I saying? Some external like person is pushing or pulling on an object. Or it could be something else. It could be like a car or a truck pushing, towing something, whatever it is. We call these forces applied forces. Pardon me. So let's say you have a person who's standing here like this, and then you have a box like that, and then you push on the box with an applied force, and the object will accelerate in that direction. Okay, so here the applied force is just a force of contact between you and the box. Okay, if this is you here, you're happy to be pushing the box, right? Okay, so that's you pushing the box, and the box is experiencing a force in that direction because of you pushing on it. Okay, now applied force can be a push or a pull. There's really not much else to say about it. Oh, I'm sorry, I'm yawning all the time. It's past my bedtime, guys. Okay, sorry about that. Anyway, listen, there's something else called tension. So this is when there's string or rope. Now, these things can, I'll put it in brackets, can only pull. Okay? See, you can grab something and push or pull it. So applied forces can be pushes or pulls. But a rope, like if we're, if something is attached by a rope, you can only pull that object with the rope. You can't push it with the rope. If that makes sense? Okay, so a string or rope can only pull. Like say, for example, you had an object, like a person swinging on a rope, like Tarzan, guys. I know that some of you say I look like Tarzan. I know, just physically, of course. But anyway, here's someone swinging from a rope, you know, and they're swinging down like this. Okay, so there's your Tarzan here. There, he's got the right hair, right? There's Tarzan. Okay, so Tarzan is swinging from the rope, and what happens is there's this force of tension that pulls him, okay, along that axis of rotation as he sort of swings in that vertical pendulum. Okay, so here we call this Ft, the force of tension, okay, in the rope. Oops. In the rope. All right. Okay, so that's the force of tension. So these are various forces that you're going to see come up, you know, over and over again. Now, before we talk about anything else, let's talk about a method for solving problems that's called the free body diagram method. I'm going to do a couple of examples for you, and then that'll be it for this one. I do have another video for you today, though, that I made during the pandemic last year. And like when you look at that video, you just ignore any talk of the homework that they give you. But like it's a good lesson on friction, so we'll talk about that. That's another kind of force. Okay, so we'll talk about a special lesson just on the force of friction, which is another type of contact force. But anyway, let's talk about a method that we use to solve problems involving forces. So this is called the free body diagram method, and from now on I'm just going to say FBD, free body diagrams. Okay, so what is a free body diagram? Well, what you do is you try to look at an object as sort of an isolated object. So we represent objects by drawing a box, regardless of the shape, okay, of the actual object. So it doesn't matter what the object is. It could be an airplane, it could be a person, it could be a dog or a cat, it could be a book on a table, right? Any object, regardless of its shape, is represented by a box on a free body diagram. Now, we draw vectors on the box indicating the forces acting on the object, okay? And the forces are some of the ones that we just listed. Now, you indicate the acceleration with a separate squiggly line, okay? And then you solve the problem using F net equals ma, okay? So this is probably like the step where you get your answer is right here. But doing this, drawing these diagrams is actually a method, okay, for solving problems. So this is a method for problem solving. Okay, and like maybe I'll do a couple of examples with you. I think I had an example here that shouldn't be there. I had an example that I put in here. I thought I did. Let's see. Yeah, I just pasted my example in there, so just a moment. Move this down here. Okay, so let me give you an example of a free body diagram. You can see I just added something there. I'm just gonna a little bit disorganized today. Couldn't be helped. We had lots of things going on after school today. All right, so before we get on to doing some examples from the homework, let me explain something to you here. Like when you're drawing free body diagrams, okay, I'll just give you a pro tip. Because I'm a pro, I'm going to give you a tip, okay? Ask yourself, 1, is there gravity acting on the object? If the answer to that question is yes, then you're going to draw that force. Now that's almost always yes, okay? And that force is straight down, okay? 2, is there any other physical contact with the object, like a rope or someone touching it, like an applied force, you know, that kind of thing. And number 3, is there friction? Okay, so when you're drawing these free body diagrams, these are the kind of things, kind of forces you're going to put on here. So you need to ask yourself these 3 questions. Now I'm going to put little question marks after them here, because they are questions after all. Okay, and then that's how you draw the free body diagram. Let me explain. Okay, let's say we have a book resting on a table. So here's a book on the table. Now this, what I'm about to draw, is not a free body diagram. It's because we're not sitting in class together that I can't show you this. Here's a table, here's a book. Now, we're going to draw the free body diagram of the book. Now pay careful attention to how I do this. Rule number one, you draw the box representing the object. So this is the book, okay? Like I said, every object's represented by a box. Now I ask these questions. Is there gravity? Yes. So I draw the force of gravity acting straight down on the object. And I remind myself that that's just equal to mass times 9.8. Okay? Now, is there anything touching the object? Any other physical contact? And there's only one thing, and it's the table. And because the table is a surface, there's a normal force. So that'll be upwards like this. Now there's no acceleration, so I'm just going to write A equals 0 in brackets like this. There's no acceleration. And that's how you draw a free body diagram. Now there's usually one additional step. You solve using F net equals ma. So let's do that. There's not much to say here. But here, if I write the net force equals, I'm going to say up is positive. So I'm going to say up is the positive direction. Then it would be Fn minus Fg, because this one is positive, it's up, this one is negative, it's down. So I'm going to subtract the negative one. So Newton's second law says ma. I replace the net force with mass times acceleration, and that's equal to Fn minus mg. Now since a was 0, that one's gone, and I get Fn is simply equal to mg. In other words, these two forces are equal in size, okay, and they're in balance. They're equal in size, but opposite in direction, so they're in balance. And that's how you do a book on a table. So that's our simplest free body diagram. All right, let's do one more. Let's say you have, and again, this is not a free body diagram, but let's say you have a person. Let's call him I don't know. I'm drawing a blank. Let's call him Ralph. Okay? No offense, Ralph. But here's Ralph. And what Ralph's going to do is he's going to push this object this way. Okay? Now that's not a free body diagram. Let's draw that over here. Okay? Of this object here that's being pushed. What forces are acting on it? Well, is there gravity? Of course there is. Where are we? On the moon or something? There'd even be gravity there. It's always straight down. Now the guy's applied force is forward, and it would accelerate forward as a result. Okay. It is in contact with the floor, so that would be a normal force. And if there was friction, the friction would oppose the motion, so it would be in this direction. That's the force of friction, if there was friction. But let's say there isn't any for the sake of argument, just for now. Let's say it's a slippery floor. There's no friction there. So this would be your diagram. And since this is the unbalanced force, you would write F net in the x direction, so in the x component of the motion, if you like, F net equals max. And that's it. Okay? That's the only equation that goes with that object. In the y direction, we're just going to get what we got before, which is the normal force, not the net force. The normal force equals the force of gravity. They have to be equal and opposite. All right, well, there you go. Now I have some examples here where you fill it in. Okay, so what we're going to do is fill in all the missing letters. Whoops, it's not reacting well today. Maybe my laptop is tired too. A, B, C. We have to fill in these missing forces. So let's go ahead and do that. Okay. Now what they tell us for the first diagram is that the net force is 0. That means all the forces acting on the object have to cancel out. So B has to cancel out this 200 newtons because it's a vertical force on the vertical plane. So we know B must be 200 newtons, but it has to be up. Okay, and then that way B and 200 will cancel out, and all my forces must cancel out because the net force is 0. Now what does A have to be? Well, A would be 50 newtons to the left. Okay, and how do I know that? Well, it has to cancel out those 50 newtons there. Okay, and the only way for it to do that is if it's 50 newtons to the left. Okay, and see how simple that is? Very straightforward. All right, so check this out. It says the net force is 900 newtons up, but we don't have any upward forces here, only a downward force of 200. Okay, so what would this force have to be to give a net of 200 newtons? Or sorry, 900 newtons up? Well, what you would do is you would go 1100. Whoops, sorry, it's glitchy today. 1100 newtons up, because 1100 minus 200 is 900. Okay, so see what I did there? And so this would be 1100 newtons. Okay, does that make sense? Okay, I will let you fill in the rest of these two. Well, actually, no. Why don't I do them? It's on the worksheet. But here, look. If the net force is 60 newtons to the left, that means D would have to be 20 newtons, right? To oppose the 80, because we have to shave some off to get to 60. Okay, and since there's no up or down net force, then letter E would have to be 300 newtons as well in the downward direction. Okay, so that's basically it. I will let you do the other ones of those. And here's the deal. I'm sorry to give you so much or whatever, but there is another video coming that I actually made during the pandemic on friction. That's pretty good, so I'd like you to watch that too. And then I have a little worksheet for you that I posted already. It's right here. I don't want you to do the whole thing just yet. Okay? So I'm trying to parse it down for you a little. I would like, after you watch the friction video, okay, give these questions a try, but you'll need to watch friction first, because friction, you'll notice that friction comes up. Now, you don't always need to watch the friction video to answer some of those, but you'll see the force of friction in there. You'll definitely need it for this question here. All you have to do is fill in the blanks. Okay, and what I would like you to do is just do pages 1 and 2 of this. I know I gave you another worksheet on Thursday, but you know, this is for Monday now, so like it's the weekend and stuff. There's not actually that many questions. Do not do the last 2 pages. Now, answers are at the very end. You'll find them there. So there you go. And that's it for now, guys. So listen, what I'd like you to do is, you know, finish the worksheet I gave on Thursday. Do the first 2 pages of this one. Don't do any textbook homework. Okay. And then we will proceed from there. Okay, moving forward into next week. And that's it for now. So there will be a video on surface friction that I will post in the group chat. It's actually posted right here, the videos, okay, on the page already. So you can see it says 11U static friction and 11U kinetic friction. So I did post these videos already. So if you want to watch them, you can just go to OneNote and tap on the link, and it'll take you to YouTube and you can watch them. Now, I'll warn you that my friction video was made during the pandemic, but I really spent a lot of time on it. I don't want to reinvent it. And so I would like you to watch it. But if I mention other students' names, don't feel sad. That was my class last year, so they're in grade 12. So you might hear a few familiar names. Okay. All right, guys. So that's it for now. Please watch my friction video too. And so it's a big lesson for today with those few things that we talked about here, plus the friction video. And we'll talk to you soon.